Alright, so yesterday we focused a lot on radicals and simplifying radicals. So as part of your warm-up today, I had you looking at some radicals and simplifying them. And now we had some radicals in which we had addition and exponents underneath the radicals. It's important to know or understand that the order with which we have to do these problems is you have to simplify the inside first. It's almost as if there's these imaginary parentheses around the 3 squared and the 4 squared. So the square root doesn't cancel those squares. You have to first square the numbers inside, then add them, then take your square root. So a big part of 1, 2, 3, and 4 was really making sure we understand order of operations and exactly the order with which we can simplify radicals. And then in number 5, we had the case of even exponent inside becoming odd outside, needing absolute values. And then I got asked, just so you know, the one homework where the answers are at the bottom, it appears the absolute values didn't transfer over when I had photocopied or typed them. So when you're checking your answers to the odds on the one radical homework, there are no absolute values down at the bottom. When we go over that on Wednesday or Thursday, there will be absolute values. So just kind of like an FYI, if you used the bottom to check it and you thought I have absolute values and there aren't any, it looks like they didn't copy over. So there should be. Any questions at all on simplifying or for our warm-up? Yes.
Okay, so when do you use the absolute value again?
So the absolute values get used if we have a radical, right? So any radical that does not have a number in front is considered a square root. That makes that radical what we call even, because a square root is technically equal to the 1/2 power, and we would say 1/2 is an even number. If the inside power is also even, and you simplify it, and the new power of the variable becomes odd, now you need absolute values. So if the inside is even, and this is also even, and we'll talk a lot more about that in chapter 6, and your answer becomes odd, then you need absolute values. So let's say x to the 26th. The square root of x to the 26 becomes x to the 13. 13 is odd, 26 was even. I need absolute values. Does that help you more? Is everybody else good with that too? I know that that's like the most confusing part. And I always call it kind of like the even, odd rule. So today we're actually starting a new type of concept, and that concept is called complex numbers. So up until this point, we've lived in what we call the real number system. As we are expanding our knowledge, we enter into a world called the complex number system. The complex number system is where we get imaginary numbers from. So let's go over our vocab and talk about what is a complex number, what is an imaginary number, and how and when do we use them in mathematics. So what I wanted you to do is consider the graph of the function x squared plus 2x plus 4. So go ahead on your graph And again, I put all of the key kind of pieces of information up there for you. Sketch out the graph of x squared plus 2x plus 4. And then we're going to answer the questions over on the left about that graph. So my vertex is at -1, 3. If I made my table of values, then they increased. It's open up. So it says consider the graph. How is the graph of the function above related to this equation? So if you look at this equation right here and we think about the techniques that we've already had, can you find factors of 4 that sum to 2? Can I factor x squared plus 2x plus 4? Are there any factors of 4 that would sum to 2? So we know to get x squared, I'd need x times x. Factors of 4 are 1 and 4, and 2 and 2. Are any of those going to fit in here somehow to get me to that number? No. So what do we call a problem like this that can't be factored? Prime. So this is prime. When you look at your graph, does my graph have any x-intercepts? No. So, if it can't be factored, and there are no x-intercepts, then we say that the graph has no real roots. Or previously you might have said it had no solutions, because the x-intercepts are another word or term for the solutions. So it says, what does this tell us about the solutions? Well, there are none, right? It doesn't factor. It doesn't cross the x-axis, so there are no solutions. Well, there are no solutions in the real number system. We're going to talk about solutions that exist in the complex number system. So here's where we've been living in mathematics. We've been living in this box over to the left called the real numbers. And it's been focused mainly on rationals and irrationals. Well, today your box got larger. Today we're going to now incorporate the imaginary numbers. So we have the real numbers and the imaginary numbers. Another way of saying the imaginaries are saying the non-reals. A complex number is the set of numbers consisting of an imaginary and real number. A complex number is written in the form a plus bi, where a is the real part and bi is the imaginary part. So we now have the reals and the non-reals. I stands for the square root of -1. I stands for the square root of -1. So anytime you have a square root of a negative, it's going to become the letter I. Anytime you have a square root of a negative, it is going to become the letter I. We call I the imaginary number system. The imaginary numbers come from the negative square roots of real numbers. The imaginary numbers come from the negative square roots of real numbers. So find the additive inverse of each complex number. If you recall, the additive inverse is the number that you can add or subtract to equal 0. So the additive inverse of -7 would be +7. The additive inverse of -9i would be +9i. So the additive inverse is essentially the opposite of the term. So in number 5, you have -5i. So its additive inverse is +5i. In number 6, we have mixed signs. The additive inverse of 4 is -4. The additive inverse of -3i is +3i. And in 7, the additive inverse of a is -a. The additive inverse of bi is -bi. So the reason that we took so much time yesterday and learned how to simplify square roots again is because complex numbers are going to involve square roots of negative numbers. So anytime you see a square root with a negative, the first thing you want to do is bring out the negative as an I. So we're going to rewrite the square root of -121 as I, square roots of 121 minus 7. And then you're going to look at your square root and simplify it. So in this case, the square root of 121 is 11. And then it says to put it in the form a plus bi. So we're going to write the -7 first plus 11i. So that it is the a, or the real part, plus the imaginary. Number 2, the square root of -18 becomes I square roots of 18 plus 7. So once again, we rewrite it as 7 plus, and we simplify 18. 18 is 9 and 2. The square root of 9 is 3. So we get 3i square roots of 2. So the I is kind of like a variable. It's going to come after the coefficient, but before the square root. And number 3, we'd write it as 7 plus the I for the negative, and the square root of 25 is 5. If you want to skip this line here, you can. Again, I'm just showing you kind of how it becomes I, and then you simplify. Okay, so we can also have square roots where we're not adding a real part to them, where they're simply square roots of negatives. So square root of -54 is kind of like I square roots of, and then you would have 9 and 6. So you get 3i square roots of 6. 2 is prime, so it just becomes I square roots of 2. You want to make sure you never leave a negative in your radical. 12, we know that 12 is the same as 3 times 4. So you'd get 2I square roots of 3. And what you're going to start to notice is as we simplify more and more square roots, we get a lot of repeating numbers left behind. You're going to see a lot of 2s, 3s, 6s, 5s, 7s, etc. And then 36 is a perfect square. So the square root of negative 36 becomes 6I. The square root of negative 36 is 6I. There are variations to the powers of I. So the very first power of I comes from the square root of a negative 1. But as we know, we can multiply, we can divide, we can subtract. I is kind of like a variable. If I multiply two i's together, I get I squared. So if I multiply two i's together, I'd get I squared. So think about multiplying the square root of negative 1 times the square root of negative 1. If you multiply the same square roots together, you get what was under the radical. So the square root of negative 1 times the square root of negative 1 is equivalent to negative 1. Which also means that if we have I squared in a problem, it is equal to negative 1. So you're never going to give an answer with an I squared. You're never going to give an answer with an I squared. I cubed, well, something cubed is like I times I times I. Or you can think of I cubed as I squared times I. But we just said I squared is always negative 1. So I cubed is equal to negative I. I cubed is equal to negative I. So you're never going to give me an answer with I cubed. You're always going to simplify it to negative I. I to the fourth could be I squared times I squared, because the rule of exponents is you add them together if they're multiplied. So 2 plus 2 is 4. Well, I squared is negative 1. So negative 1 times negative 1 is 1. I to the fifth would be like I to the fourth times I. But I to the fourth is 1. So I to the fifth is I. I to the sixth. Well, 6 could be 4 and 2. I to the 4 is 1. I to the second is negative 2. What are you starting to notice about our problems with i's? I to the 1 is the same as I to the 5. I squared is the same as I to the 6th. I cubed and I to the 7th are also going to simplify to be the same. So that becomes negative I. I to the 4 and I to the 8 are the same. That pattern is going to continue forever and ever and ever. The i's fall into an infinite loop of a cycle of 4. So what that means is every 4, it goes back to the beginning. So like I to the 9 would be the same as I to the 10 would be the same as I squared. I to the 12 would be the same as I to the 4. So we can simplify higher powers of I to fall into one of the first 4 patterns. So what you do to simplify these without having to count through your cycles of I is take the number here, so you're going to take 13, and you're going to divide it by 4. So 4 goes into 13 3 times. I don't really care about the 3. What I care about is the remainder, which is 1. Whatever the remainder is when you divide by 4 is the part of the cycle you are in. So I to the 13 is the same as I, because it's the first term in the power of 4. So same with the next one. You take 4, divide it into 11. So we know that 4 goes into 11 twice. That's 8. So we get 3. That remainder of 3 tells me that I to the 11 is the same as I cubed, but I cubed is negative I. So I to the 11 is negative I. Okay? 4 into 91. Well, 4 goes into 91 at 88. So 91 minus 88 is 3. So I to the 91 is the same as I cubed, which is negative I. Okay? I to the 244. So 4 goes into 244. Do you remember how to do long division? And again, I know a lot of you have calculators too. But again, it would be, okay, 4 into 24 is 6. So you get your 0, bring down your 4, and you get 61. So now what happens here is I get a remainder of 0. If I get a remainder of 0, that means that this is like I to the 4th, which means this is like the number 1. So a remainder of 0 is like being on the cycle of I to the 4th. Yes?
How did you get I?
Because my remainder is 1. So that's like I to the 1. But like anything to the first power is the same as itself. So 10, we get subtracting 8, so we get a 2. A remainder of 2 is I squared. I squared is negative 1. You cannot add I cubed and I to the 6th. You cannot add their exponents. Just like if I gave you x to the 6th plus x cubed. That does not equal x to the 9th. I to the 6th plus I cubed does not equal I to the 9th. So what you have to do is simplify all the parts of I separately. So I to the 6th is negative 1. I cubed is negative I. So I to the 6th plus I cubed is negative 1 minus I. I to the 6th plus I cubed is negative 1 minus I. Where negative 1 is your real and negative I is your imaginary. That is a perfect example of a complex number. So again, it's important to understand the vocab. A complex number is the sum of a real and an imaginary. An imaginary is the part of the complex number involving the I. Because sometimes we confuse complex number and imaginary number. A complex number is the sum of a real and an imaginary. The imaginary is the part involving the I. So your homework is the next 2 pages in your packet. It's not a front and back this time because our notes were 3 pages. So you are doing homework day 1, last night's homework, which was the simplifying radical expressions, and those 2 pieces of that worksheet are due tomorrow morning. And then because the I's are quite complicated, especially with the cycles, there's a delta math, so you can kind of get some instant feedback, work through the cycles of I, work through simplifying just square roots, and that will be tomorrow. On Thursday, we'll come back and look at day 2, where we're going to like FOIL I's, we're going to add, subtract, divide by I's. We're going to really get into all the different parts and powers.